Thank you. So, we welcome you to our next season of AgScience-on-Tap. And this semester, we are going to talk about the soil as a foundation of food production. But before we start, and there are flyers with all the dates hanging outside, but also on our website. And I want to remind you, on Saturday, we have the Farm Vision Festival on campus. And you can see a lot of things all around agriculture with talks, with activities. Just come along and look and see. It's fun for the whole family. So every age finds something to do, from milking a cow and I don't know. So just drop by. It's going to be a lot of fun. And so today we start with the soil as a foundation of food production. And our first speaker will be introduced by Monica.
Okay. Yes, thank you. Also from my side, for those that don't know me, my name is Monica Egger, and I'm a professor for urban productive ecosystems at the TOM. And yeah, this is our second year with Ag-on-Tap, second summer semester, and we're really excited about the topic of soil. We also have some new soil scientists at TOM, some of them in our own group in the last year, and also a new professorship. And yeah, so we are very excited to open this series with Dr. Franzi Buka, who is a postdoctoral researcher in soil science at the Technical University of Munich. Since 2021, she has been a postdoc. And before that, she did her PhD. She has a Dr. Rare Nut in soil structure formation, initiated, or on the topic soil structure formation, initiated by biochemical processing of organic matter. And so her research focus is on soil structure development, stability, and turnover with respect to organic carbon. And so her aim is to create knowledge and conceptual understanding of the complex processes involved in soil structure formation, stabilization, and disintegration. Sounds like some very big words that I look forward to deconstructing, or deconstructing today. And so with this knowledge, Franzi hopes to help us to engineer soil development in marginal lands and post-mining landscapes. So I think this is a really important topic when we're thinking about habitat restoration. And so aside from doing pretty cool research, like we already see here with the fancy Bodenkunde red bus that I'm also a little bit jealous of. This is pretty boring. She also teaches soil pollution and remediation at the postgraduate level. She teaches soil classification and a lot of field courses, and she teaches laboratory methods for soil analysis. So she has a master's in science and also a bachelor's of science all around soils. And I think we are very, very lucky and grateful to have Franzi, Dr. Buka, as our first speaker of this soil-based series. So the title of her talk, I'll just read it out and then give her the floor, is From Dust to Soil. What makes a functional, stable soil, and what does organic carbon have to do with it? So thank you so much, Franzi, for being here today, and we're looking forward to your talk.
Okay, thank you. Really great introduction. Really massive. So I try to keep it a little bit simpler. So we go from simple to more complex. I'm really happy to be here, and I think this is a great lecture series. And I'm really happy to start with the first talk about soil. And we focus today more or less on soil as a basis for food production and agriculture. And for this, we need usable soils. So we need soils functional and ready to use for agricultural practices. And for this, I would just like to start with a rhetorical question. Is this a functional soil? I don't think so, yeah? So I think you don't see plants, you don't see natural plants growing, you don't see probably not enough water. And if you imagine like a machine tilling the soil, it would get lost probably, yes. So I think it's not enough stability there. And when we move on forward, then we have a soil like this. Is this a functional soil? So we don't have a desert anymore, so we would have water. And we also have some kind of sand castles that can be stable in a kind of way. So, but still, these sand castles are not really stable. So if you pour water on them, they would fall away. Or if we drive there with a tractor or machinery, that would also not withstand the heavy machinery. So the question remains, what do we need for this kind of soil? So what do we need that the soil is ready to use and ready for agricultural use? And the difference here is basically soil structure. So this is what you see here. So the rough surfaces, all these clumps and crumbles is basically soil structure. And this is what makes the soil stable. And this is what makes the soil stable for agricultural use. You can grow plants there, they find water, you can till it, and you can like it withstands erosion, so it doesn't go away when water is running. It's not blown away by wind or when a heavy storm is working. So this is what we need. And now we just want to have a closer look into that and see what it's made of. This soil structure is basically made of these small clumps. So these clumps are held together by some binding agents. And without these binding agents, we just have basically sandcastles. They go away. We have just desert. You can't form anything that holds together. These binding agents can be organic or inorganic. So the inorganic we today keep a little bit aside and focus on the organic part, just that you know, okay, there's both of that. And these binding agents lead to an arrangement of the soil components into a stable structure. This is what holds the soil together and forms these clumps that are stable and ready to use, basically. Yeah, if we zoom in a little and dig a soil profile, this is what soil scientists love to do. You have like a large hole, a typical soil profile, and you also have vegetation cover on top. And you see like here's the soil structure. You also can imagine, I think everybody was digging into soil. So you see that when you take that out, you feel these clumps, they hold together, and you can break them down, but they have some kind of stability, some more and some less. And if you zoom into this kind of structure, then you really see that it's quite a complex network. So colleagues of mine did a really nice micro CT image of a soil cube, really tiny. And like this micro CT images shows really the complexity of this structure. So the white is mineral, and black parts is where the X-rays went through. So this is pore. And there's like a false color, like the roots inside this soil cube were colored. So they're not colorful in the original image, they were just colored to make them more visible. And when you just basically have a look on that, you see this is quite interesting to see because it's a really complex network. There's pores, there's minerals in between, there's roots also creating pores, and everything works together somehow well organized, and everything is functional. So the root gets water through the soil pores. Microbes can probably also live within this space, and water and air can penetrate as well. When we just put that thing into numbers, we see basically that the soil is half a natural soil in our environment is half pore space and half soil solids. So the pores can be filled by water and air. This is where the processes happen. So we have a complete network. We have these pores, water flow through the pores, and also air-filled pore space, which is really important. And half of that is actually mineral, so by volume. So these minerals are somehow arranged and bound together by these binding agents. And today we focus on the organic binding agents, which is actually by volume just a tiny fraction of the soil, and by mass it's even less because organic matter is not really heavy. So, but just this tiny fraction of the soil is this what we need. So what actually binds the soil together and what brings the structure and the features. Yeah, so just a general introduction about the organic matter in soil. So basically, it's all fixated CO2 from plants. So it all starts with carbon dioxide in the air, is assimilated in the plants. They build the biomass out of it. When the plant dies, so when plant litter falls, it ends up on the soil surface. It's mixed into the soil surface by animals, or we have harvest residues just entering the soil in the same way, and as well riser deposition. So roots also exudate a lot, so they exudate small carbon molecules. And also when the root dies, there is carbon, like litter, carbon source directly in the soil. So this is everything that forms the soil organic matter. And so we have the components like the plant litter directly entering. We have the rhizo deposition, also kind of litter and small compound molecules. And what is not shown here, but also really important, we have a lot of microbes in the soil. So the microbes degrade all these plant materials and litter, and they die as well and form as well soil organic matter. And so this is what we want to have, right? So we have CO2. This is also important in terms of carbon sequestration, fixated, ending up in soil and being fixed there. And so we want to have this gluing agent and this organic matter, which brings a lot of positive features in the soil. How can we lose it? Like by leaching. So leachable dissolving compounds can go into the groundwater, or if it's eaten by microbes and transferred as CO2 into the atmosphere again. So, but now we know it's important. Now we just want to store it somehow. And soil scientists basically distinguish between particulate and mineral associated organic matter, which is just referring to the storage or the long-term persistence of the organic matter in soil. So when we imagine soil organic matter enters the soil as litter, we call it POM, meaning particulate organic matter. And this is really pieces. You really see that. So this is a tiny fraction. You see that with the naked eye. And it can be degraded by microbes. It can also be eaten or degraded by other organisms. And when it's getting smaller and smaller and smaller and more degraded, or maybe already went through an organism, then we call it mineral associated organic matter. It's so small and so degraded that it can adhere to minerals. And this is what we consider as quite stable in the soil, because it's so attached and glued to the minerals that it can glue minerals together, and it cannot be eaten easily anymore by the microbes. Of course, this distinguishing is not always like it's 100%, because there's small POM as well, and there's MALM that is also quite unstable, but this is basically the principle. Yeah, so we basically want to focus on this part now, because this is like what is the gluing agent, basically. Yeah, so how does this look like? So we have the soil cloth or the aggregate. So scientists call it always aggregate. So this is what you know, basically. You can go out, you can take a clump of soil, you can break it down into individual pieces, and this is the soil aggregates. If we zoom in really, really much in, so if this is 100 micrometer, then we have a compound structure like looking like this. So this is like to take the soil clump, like this, basically break it down into tiny pieces, and then you have a look in the scanning electron microscopy. And then you have a structure basically like this. You see again, there's mineral particles of different size, and also probably some like mixed stuff that is this gluing and cementing agents just binding these particles together. And this can be organic and also inorganic, but mostly like here is the focus on the organic. So this is really encrusting these particles and really going in between and really bridging the particles to a stable structure. And when we even zoom more in, then we find structures like this. So we have here still these mineral particles, and we have like these fine ropes. You see that basically, I think maybe from behind as well. So this is like fine strings and ropes. This is actually fungal hyphae. So it's just a tight network of fungi like growing in between the soil pores. So imagining here you have a mineral and pores in between, and the fungi, they just grow, and it just like to explore the pores and live there and find their like resources as well. And by this growth, they just enmesh the particles and bind them together. So it's probably not really very stable, but it's stable enough to form and enmesh also aggregates, because you imagine this is really a tiny, tiny scale. And on this scale, they are often strong enough to bind the particles together. Yeah, so now we basically know how structure is formed, or how structure looks like, but we don't know a lot about how the structure is formed, and especially not in a self-organizing way. So how organic matter is actually forming this structure. And for this, I just want to show you a part of my own research, where I was actually trying to find out how this organic matter really contributes to the development and formation of soil structure. For this, I started with artificial soils without any structure, just to investigate structure development from the scratch. So I had several mineral mixtures of resembling a natural soil, like imagining you have a natural soil, but you break it down completely. So you remove all organics and remove all structure. And so like this is the imagining. I started from the other way. So I just had minerals that were like just separated from each other with different size. So they had different textures, meaning that the particles had different size. So we had the clay loam texture, meaning the particles were really, really small, and just some larger particles were in between, over an intermediate state and over to a sandy loam texture, meaning there is like less small particles and many, many big particles. Yeah, and then I wanted to investigate organic matter. And for this, I just added separately different types of organic matter, just to find out how this works together and how structure can be formed by this organic matter of distinct types. So, and for this, I chose typical organic matter, which also can be found in soil, but it's nice to investigate it just separately. So I had this POM, the plant particles, in small and large size. I had dissolved organic matter, so that it was really, really small and liquid, and bacterial necromas, so that bacteria, like if bacteria would grow in the soil and would die and would also form organic matter. And then I just incubated it for a month, and so mix it all together and just kept it constant, let the microbes also eat the added organic matter, and just had a look on the structure formation later. So how could this organic matter, the microbes and the minerals work together and form somehow a soil structure like we find it in a natural soil? So just to find out how is the mechanism that the organic matter can stabilize the soil structure and how these clumps are actually formed. Yeah, then we have a look on the aggregate formation. So here, it's just the different textures. So really, really tiny particles in the clay loam, intermediate state, and the sandy loam, and with the really, really large particles. Just because it's a matter of time, we just focus on the sandy loam here, because the picture is more or less the same everywhere. And here we just compare, like we have this one textural class, so a lot of large particles, less small. This is the original texture, like the distribution of the particle sizes. Then we have a treatment with no addition, and we have the different organic matter treatments. And interestingly, so with no addition, no aggregates are formed. So you have some kind of, like in a sandcastle, when they can be formed in a dry state, but if you throw them in water, they just melt away. So like the sandcastle. So you have a particle, you throw them in water, it's just like melting. But when you have any kind of organic matter, it doesn't matter if it's liquid or bacterial or this particulate organic matter, you have suddenly, like this red bar is like much higher. So we have suddenly the stable clump formation. So we have stable aggregates formed. They can withstand water. And especially in the particulate organic matter, which is quite interesting. And when we had a closer look on the bacterial population or the microbial population, I saw that is not only the glue, so it's not only interacting with minerals itself, but there were also a lot of fungi growing. So actually I saw these ropes, just this POM could induce this fungal growth and could induce this larger aggregate formation. But interestingly, it also worked without the fungal growth, because in the bacterial treatment, we also had this aggregate formation, so this formation of these small chunks and glues, aggregates. But here, no fungi were growing. So this bacterial necromos just induced the growth of bacteria, and they didn't have hyphae. So the mechanism must be something different. And here I just had a microscopic image, like trying to look closer into this aggregate, finding out what the mechanism is. And here we just see like how the structure is actually formed. So maybe it's a little bit difficult to see. So here, this is the large quartz grains, these black parts. And then we have the pores in between. And then we have here like a matrix. A matrix, this is so shiny bluish. And I added a stain that is staining DNA. So everywhere where we find DNA, we see a bluish color. So it's not perfectly visible here, but you see that here's always like an intermixed state of this bluish, grayish, brownish color. And this tells us something here. So we have here this large sand grain, we have here another sand grain, and here we have kind of a bridge of this organic and mineral matrix. So the microbes, we don't know if they're dead or alive, because it's just staining DNA. So also dead microbes have for a while DNA. So we just know that they have been alive maybe. And so they're forming this kind of bridges. And this is what also holds particles together. So we have like this glue, organic mineral glue that is like just enmeshing or bridging even large sun grains. And also we find a little bit about the lifestyle of the microbes, because we see that they're mostly growing towards the pore lumen. So they grow there where they are in contact to air and water. So they really like to live there. And by their growth, by their living, they also excrete substances that form somehow this glue and these glue patches. Yeah, okay. So now we know, just adding organic matter and making microbes grow, we can form these water-stable aggregates. This is really good in terms of soil structure. So for example, water erosion would be prevented if we have organic carbon in the soil. So we have these glue patches, and then the soil is water stable, so it wouldn't run away just when it's raining on top. But we also need a second stability measurement for a real stable soil. We also need mechanical stability. So we need a soil to be stable against tillage. We need the soil to be stable when there is a tractor driving on top. And so therefore we need another measurement than just the water stability. And I tried this by measuring the mechanical stability of the formed aggregates. So I did this with force sensor crushing the aggregates down. So they were just placed on a table, and then a moving cylinder was crashing them. And by crashing, we were recording these force curves. So it's a little bit difficult because they're read from right to left. So you just imagine the moving piston moves down, and when it hits the aggregates, a force is recorded, because then you have a resistance. And when like the force is increasing and then a crack appears, and meaning that the force is declining, but the piston is still moving until it hits the aggregate again. And so it's like this kind of peaky curve. In the end, we can add the whole force towards work, which is needed to crush the aggregates down. And we can sum that up for the different textures. So we again have this clay loam, loam and sandy loam texture, and the force or the overall work that is needed to crush the aggregates down. And here I didn't distinguish between the different organic matter sources because there was no difference. So the only thing that was making a difference was the texture. So just the pure particle size. So the ones with the small particles were much more stable than the ones with the larger particles. This is probably because there were just more contact points like present, that makes the structure more stable. So it's maybe a little bit more brittle, but it's just can withstand more force. But the interesting thing is when we have a look on the overall numbers, it's crazy low. So these artificial aggregates are 10 times lower or less stable than natural aggregates, which are extracted from the soil, the same texture, and same composition basically. So this was quite a surprise, yeah. So I had really rapidly these water stable aggregates and thought, okay, organic matter is really useful for that. But this mechanical stability, I don't have any mechanical stability. And so this is definitely two mechanisms. So we have basically one simple formula. We have a mineral mixture, any kind of minerals, doesn't matter what large sizes they have. We add organic matter and we get aggregates, water stable aggregates. So without organic matter, no water stability, the sandcastle is just melting. With organic matter, we have water stable aggregates. But if we crush them down, they have really a minimum mechanical stability. So this is definitely two different mechanisms, and we definitely need both for a stable soil. Yeah, and then just to having a quick outlook on the last slide. So now we know a lot about the formation on soil structure and know a lot what happens when we add organic matter. And then so the question was, can we transfer this knowledge? Can we transfer this knowledge to engineer soils where soil structure formation is urgently needed? And for this, I want to take you to Australia. So the red dot is here. So where a lot of open pit mining happens. So this is like lignite mining, brown coal mining in open pits, meaning that really, really large holes are excavated more or less 80 meters deep to reach the coal seam. And then all this overburden material, the material that lies above the coal seam, is just excavated, put on a huge heap, and then the coal is extracted. And later on, when the coal is finished, you just have to restore the landscape somehow. You see the magnitude here, this is 1 kilometer. So this hole is really, really huge. And just in the end, you have a landscape that needs to be restored and also needs to be restored quickly because you want to grow something again and you want to have a stable structure because often you have slopes. You don't want to run them away when there's a little bit of rain. So you want to stabilize the slopes. So the idea was also just to use this concept, like we know now, which is basically need organic matter to create soil structure and to find out if that works as well. And the nice thing, it worked in the same way. So we have this overburden material and we add some kind of organic matter sources. We add plant litter, you know that already. But in Australia, I think people are maybe a little more innovative, or I don't know. So they had also really nice ideas what can be added as well. So they added a little bit of the original brown coal. This is also organic, but much more stable. Then they wanted just to reuse some waste products. So they added some paper mulch, which was like just a leftover from a paper factory, which was close by. But in the end, it's also just carbon, right? So it's some wood, lignite structure, and a little bit of ash, also from the coal firing plant, which also adds nutrients to the soil. And then I just tested the whole thing in the same setup and had basically the same results. So when microbes were growing, especially when plant litter was added, which could really be eaten by microbes really quickly, I had the same results. So I could really, really form a stable soil in quite a short time. And this is especially cool when from a soil science perspective, because we always think soil formation takes ages and takes 10,000 years or whatever. And yeah, we still see that the soil what we have is not the fully functional soil because we have some qualities missing, but it's just first step into the right direction. Okay, then just to wrap it up, now we have a broad overview about how soil organic matter contributes to soil structure. First, okay, organic matter is needed for bridging this or binding the particles together. We want to have these stable aggregates, which makes the soil functional. And we see that the microbial degradation of organic matter can form these bridges. So we saw these bridges formed also by just microbial biomass. And we know that this organic matter can form water stability, so probably provide resistant against water erosion. But this mechanical stability, so stability against tillage or whatever, possibly relies on other mechanisms. So maybe the inorganic worms, we don't know. And in the end, so we can really use this knowledge, for example, to engineer or design stable soils in young landscapes where we really need to quickly restore a functional soil. Okay, so thank you all for listening.